Hi everyone, this is Marvin Paul, the Chemistry Guru. Now in this week's video, we want to learn how to compare solubility of silver phosphate in different solutions. So let's take a look at this question. In which of the following solution will solid silver phosphate be the least soluble at standard temperature? Given that the numerical value of KSP is 8.89 times 10 to the power of minus 17. So we have 4 permutations here, and we will try to calculate solubility for each of these solutions, and we determine which is the smallest value, since the question is asking me for least soluble solution. The topic tested in this question obviously is under solubility product. Dissociation involving silver phosphate is given here. Ag3PO4 will dissociate to give me 3 Ag plus and 1 PO4 3 minus, and my solubility product or KSP term will just be the concentration of my product raised to the power of the coefficient. So KSP will be Ag plus concentration power 3 since I have 3 Ag pluses, PO4 3 minus power 1 since I only have 1 PO4 3 minus. And the question tells me that the KSP value is 8.89 times 10 to the power of minus 17. And since we need to determine solubility in each case, so let solubility be X or any letter that we want to represent solubility. So the first one involving part A, how do I determine solubility of this salt in pure water? So this is the most straightforward question because that is one of the first few things that we learn under solubility product. When you're given KSP, can you calculate solubility and vice versa? And obviously, we are referring to solubility in water when there's only that salt dissociating to give me a concentrated solution. So when you have Ag3PO4, dissociate to give me 3 Ag plus and 1 PO4 3 minus. And if X is solubility, solubility is how much salt you can dissolve to give me a saturated solution, and therefore it is always with reference to my salt. So X, it is with respect to salt. So mole ratio involving your dissociation of silver phosphate is 1 salt will give me 3 cation and 2 anion. So X, concentration of my salt, will dissociate to give me 3x concentration of Ag plus and x concentration of PO4 3 minus. 1 is to 3 is to 1, x is to 3x is to x. So I know that Ag plus concentration will be 3x. I can sub this into my KSP term. My PO4 3 minus concentration is x. I can sub this into my KSP term. So my KSP will be 3x power 3 multiplied by x, which we can rearrange this to 27 multiplied by x to the power of 4. Then I can rearrange it, I can solve for x. X will be KSP divided by 27 power 1 over 4, which is equal to 4.26 times 10 to the power of minus 5. So this is the solubility of silver phosphate in water. Next, how about B? B, when we have 0.1 mole per dm cube of AgNO3. Now we notice that AgNO3, it is a soluble salt, since nitrates are soluble, and you dissociate fully to give me Ag plus and NO3 minus. And 0.1 concentration of AgNO3 will give me 0.1 mole per dm cube Ag plus and 0.1 mole per dm cube NO3 minus. Of course, we also have to consider the dissociation of silver phosphate. Same thing, the dissociation of my silver phosphate 1 is to 3 is to 1. So if X is solubility for my salt, then X concentration of my salt will dissolve to give me 3x concentration of Ag plus and x concentration of PO4 3 minus. Now you notice both of these salts, AgNO3 and Ag3PO4, both of them will dissociate to give me Ag plus. So we will call this the common ion. And under solubility product, we have learned that the presence of the common ion will suppress solubility. So later, we actually understand that since solubility will be suppressed in presence of my common ion because of my AgNO3, then later the value that we are calculating involving solubility in part B has to be smaller than what we have determined in part A, because part A is just the dissociation of your silver phosphate by itself, and we have already determined solubility in the presence of my common ion. Then I'll expect solubility for silver phosphate to be a smaller value than 4.26 times 10 to the power of minus 5. So we actually can apply this approximation. The total concentration of my Ag plus will be 0.1 that comes from your silver nitrate and 3x that comes from your silver phosphate. But since your silver phosphate is a sparingly soluble salt, the extent of dissociation is very small. So x, it is a tiny value, and therefore 0.1 plus 3x will just be approximate to 0.1. 0.1 plus 3 times 0.000000 something, which is a tiny number. If you round this off to 4 significant figures, 5 significant figures, this 3x wouldn't come out even if you do rounding off. So I can just say that, okay, this will just be approximated to 0.1, or I can say that the Ag plus concentration will just come from the fully soluble salt, which is in this case my AgNO3. Now I can sub this Ag plus, which is 0.1 concentration, into my KSP term, and PO4 3 minus will still be X. There's only one source of PO4 3 minus that comes from the dissociation of my salt. So PO4 3 minus concentration will still be X. Ag plus concentration will now be 0.1. I have an expression involving KSP and solubility. I can solve for that. X is equals to KSP divided by 0.1 power 3. So X will be 8.89 times 10 to the power of minus 14. Again, we notice that this value that we've calculated in part B is a smaller value than what we have in part A. So this is consistent with the common ion effect. Presence of the common ion will suppress solubility for my sparingly soluble salt. Next, how about part C? Involving part C, when I have 0.1 mole per dm cube ammonia. Now, maybe at the beginning when we look at ammonia, we might not recognize what is the purpose of it because it is not a common ion. But what ammonia will do is it actually form a diammine silver complex with Ag+. And this diammine silver complex Ag++ plus 2 ammonia to give me Ag NH32 overall positively charged. What this will do is it will actually lower the concentration of Ag+, and it will decrease the concentration of my product involving the dissociation of my silver phosphate. And according to the Charteris principle, when there's a decrease in the concentration of my product, position of equilibrium will shift towards the right hand side, favor the fall process, which means that I'm favoring the dissociation of your salt, and I'll expect more of the salt to dissolve, so solubility of Ag3PO4 will actually increase. Now for this question, we will not be able to calculate the increase in concentration because we know that Ag plus with ammonia to give me diammine silver complex, it actually favors the forward process. But since I don't have information involving the equilibrium constant term, I will not be able to do calculation involving what is the change in the concentration of Ag+, and therefore I will not be able to calculate the new solubility of AgPO4 in presence of ammonia. So this is involving part C. Now finally for part D. Part D is another common ion. In this case, I'm adding 0.1 mole per dm cube sodium phosphate. So we should recognize that I am adding PO4 3 minus. So same idea here, 0.1 mole per dm cube of your salt will give me 0.3 mole per dm cube of Na plus and 0.1 mole per dm cube of PO4 3 minus. And same thing involving the dissociation of your silver phosphate. It will give me 3x concentration of Ag plus, x concentration of PO4 3 minus. Now my common ion is phosphate, and the total phosphate concentration will be 0.1 plus x, 0.1 that comes from the sodium salt, x that comes from silver phosphate. Then we will impose the same approximation here. We will say that, okay, since your silver phosphate is sparingly soluble, the degree of dissociation is very small, so therefore x is very small, and 0.1 plus a tiny number is just approximate to 0.1. I don't need to consider the dissociation of your silver phosphate in the first place. So therefore, we can approximate PO4 3 minus concentration will be 0.1. So we will take it that all the PO4 3 minus will come from your sodium salt that is fully soluble. Then we can sub this into my KSP term. The Ag plus concentration will still be 3x. PO4 3 minus concentration will now be 0.1. So my KSP expression will be written as 2.7x power 3. And therefore I can rearrange, I can solve for x. X is KSP divided by 2.7 cube root, which will give me this value 3.21 times 10 to the power of minus 6. So quite a bit of calculation here, but we have finally gone through all the solutions involving solubility for silver phosphate in each of these solutions. Involving solution A for pure water, solubility is 4.26 times 10 to the power of minus 5. B, in 0.1 mole per dm cube AgNO3 in presence of a common ion, solubility is 8.89 times 10 to the power of minus 14. C, we cannot calculate it, but we do know that solubility is going to go up because of complex formation. I'm removing Ag plus concentration, so it will trigger the dissociation of the salt to try to top up the loss of my Ag plus concentration. Finally, D, 0.1 mole per dm cube Na3PO4, the solubility is 3.21 times 10 to the power of minus 6. So if you recall, the question is asking for lowest solubility. So in this case, the answer will be option B. Alright, so that was the discussion involving this question. If you have learned something useful from this video, please give me the thumbs up, like this video, and subscribe to my YouTube channel for more weekly video lessons. That's all for now. I'll see you next week.